Dear students, welcome back to the St. Joseph Composite PU College, Vijaypur. I'm Rahul, and in this video, I'm going to explain you that the vapor pressure of a solution of a non-volatile solute in volatile solvent. Okay, and for this, I need a container. Let me have a container here. Okay, this is one container. Actually, I needed two containers here. Let me have one more container here. Okay, these are the two containers. Now, just I want to show you that how the solvent molecules and solution molecules are arranged. Let's understand with an example here that if in this container, if I put a water, this is the water surface in both the containers. So for our convenience, I just use that these are the water molecules. You can see that how the water molecules are systematically arranged at the surface. Even at the inside, the water molecules are arranged. The same thing is there in this container also. 1, 2, 3, or some molecules are arranged here, and some molecules are present inside. They are present randomly. Now these are the two containers containing pure solvent. This is a pure solvent. Pure solvent is there, and I was explained that in the pure solvent, the number of molecules present at the surface are more molecules. So only I am discussing about solvent molecules. There are more solvent molecules. Therefore, this implies here more vaporization. Okay, and therefore I will show some vapors here. The vapor. So this is what we get, the vapor. It's a vapor creating a vapor pressure. Here. Okay, you can say that more vapor pressure will be there because more vapor is there. Now in the second compartment, what I will do that I will add here some solute, some kind of solute I will add, and those solutes are occupied the surface as well as they are dissolved in the solvent or forming here a solution. Okay, now in this case, the number of solvent molecule at the surface level, number of solvent molecules at surface are less. There are less numbers. So because of that reason, there are less vapor is created because surface area is reduced there. Therefore, you can say that vapor produced, but that vapor is very less. Okay, this is what vapor we have here. So these are the vapors. So compared to this compartment and this compartment, here the few vapor molecules are there, and therefore the less vapor. Okay, let me change this. Less vapor pressure. So why less vapor pressure? Because here the less vapor is produced. No, why less vapor is produced? Because the surface area is reduced there due to the presence of non-volatile solute. Okay, now this part we have to explain in terms of equations. Now assume that only this part, this container we have to consider. In this container you have to see that there is mole fraction solute, the mole fraction of solute, mole fraction of solute can be given as XB. It's a mole fraction of solute, and then mole fraction of solvent, because it is a solution, right? In that two components are a mole fraction of solvent equals to XA, or you can say mole fraction of XII. The pressure created at this point, it is taken as P. Okay, pressure created is P, and this pressure can be given by the using Raoults law, that is P is equal to P naught A into XIA. Okay, XIA is what? The mole fraction of solvent. This is what we get a pressure here. But the fact is this XIA is not, you can say we don't need in this equation, we need the solute particles. As I increase the solute particles, or you can say that non-volatile solute particles, then what happens here? The surface area reduced again, the less vapor is produced, less vapor pressure will be produced. Okay, and therefore we have to express this pressure or vapor pressure in terms of mole fraction of solute, not in terms of mole fraction of solvent. And for that, what I will do that I know that one thing, that is xi of A plus xi of B equals to 1. I can write here xi of A, like xi of A equals to 1 minus xi of B I can write. Okay, now I will fill this value taking this equation as 1 and this is equation number 2. Then comparing equation 1 and 2, we can write here the P equals to P naught of A, and that should be multiplied by 1 minus, okay, xi into B. This is what we get equation. Again, we will simplify this. P is equal to, P is nothing but a total pressure here, P naught of A minus, we'll multiply with this, we get then P naught of A into Xi B. Xi B, once again I will repeat, it is the mole fraction of solute. Mole fraction of solvent it is not, it is mole fraction of solute. Keep in the mind, it's important because most of the students get confused with this. Now we'll take P naught on the other side, it becomes P minus P naught of A, and that equals to minus P naught of A into Xi B. I'll multiply the whole equation with the -1, and by that what I get here, P naught of A minus P is equal to, plus the minus is multiplied here, therefore it becomes plus P naught of A into Xi B. Now if I want to write the equation in terms of mole fraction, then it becomes P naught of A minus P divided by P naught of A is equal to Xi B. Now there are two terms are there. You just notice here, numerator and denominator. In the numerator we have P naught A minus P. Initially there have some amount of partial pressure that is given by P naught, but when you dissolve some non-volatile solute in that, the pressure reduced. Okay, that is nothing but a partial pressure. The partial pressure of that solvent reduced from the original. This is the lowered vapor pressure. How much it is lowered we can calculate. It is initial minus final. It is solvent plus minus solution. This is lowering of vapor pressure. Lowering of vapor pressure it is. Okay. Now we have to compare with the initial value. So therefore we have here P naught A. We have the term here P naught of A minus P divided by P naught of A. This is numerator is lowering of vapor pressure, and that we are comparing with the initial value, that is pure vapor pressure of pure liquid, and that is directly related to the mole fraction of solute. Let me write once again, clear you that it's a mole fraction of solute. Mole fraction of solute. Mole fraction of solute it is. Okay. Now because of this reason, the Raoults law can be stated here in a different way. This statement is for the you can say that solution containing non-volatile solute. Okay, so therefore Raoults law for solution containing non-volatile solute in volatile solvent. Okay, we have to write all the things completely here. Okay, we have to clear the concept here, and therefore what we get here, the statement is that is this term, this whatever the term is, that this term is called as relative lowering of vapor pressure. Relative lowering of vapor pressure is equals to mole fraction of solute when the solvent itself is volatile, when solvent itself is volatile. Okay, this is the equation, student. Only thing in this you have to remember, that is this equation, that is P naught A minus P divided by P naught A is equals to mole fraction of P. This is the equation you have to remember, student. Okay, hope that you understood this concept. Then thank you for watching this, students.